Okay. All right. So this is the midterm two topics document on Canvas right now. And yeah, happy Friday. We'll see. I guess we'll see you guys next week. Wednesday for the midterm. I'll send out another seating chart. And yeah, it'll be here. Pen and paper exam. Oh, you know what? Maybe I need to write. Bring a calculator. Where do I put that? Okay. Well, anyway, I think. Okay. Well, anyway, bring a calculator. So, and you can have one sheet of notes. All right, front and back. Do I need to say anything else? I think that's about it. Okay. All right. So I've got 6 things listed, and I will probably pick 4, maybe 5, depending on this thing. I think if I try to fit all 6, I think it's going to be too much to fit in 50 minutes. So, and then I'll try to pick reasonable numbers that you can like do the multiplication in your head rather than, I mean, obviously if you get the calculator, you can type the things in the calculator, but it's a lot easier to do like 2 times 3, or, you know, even if it's like 2.1 times 3, that's relatively simple versus like 8.7 times 6, you know, like that's a lot, whatever, you know, so they're both just 2-digit numbers, but some are much easier, right? Okay, so anyway, one is the calculating a numeric gradient manually. All right, so I'll have like this really simple neural network set up, and the activation function is, well, also I'll keep it simple. It'll either be the identity function, so it's just x, or the ReLU, which is the identity is for positive values of x, and it's 0 for negative values of x. Okay, or I mean less than or equal to 0. So, so you know, no like plugging into sigmoid or anything like that. Just either just leave it as is, or maybe turn it into 0. Okay. And so you'll do, you know, forward feed or whatever, and then you'll perturb one of the values, and then you'll do forward feed, and you'll see how much the loss function changes. Loss function will be either the mean squared error or the sum of squared errors, you know, and, you know, the way you calculate your loss function is you have to do it for all of your observations. And so to keep this simple, I'll probably just give you 2 observations, okay? So at least you do like this observation, and you get a prediction, and you square that difference, and then you get the next observation, you get a prediction, and you square the difference, and at least add them or average them or something like that, okay? And then I'll set initial weights and biases, try to use simple numbers there, okay? And you'll figure out what the numeric gradient is. So that will be that. Okay. Neural network, I might ask you to calculate the analytic gradient. And so again, a very simple neural network. And again, here, the activation function will be the identity function. We'll keep it simple here. Loss function, mean squared error or sum of squared errors, probably mean squared error, and then and I'll have a set of two observations. Okay, give you the initial set of weights and bias matrices if we include bias matrices, and then I will ask you what is, you know, what's the gradient? I guess dj dw. I guess if it's like if it's the original loss function, it'll be like a factor times dj dw. Okay, and you know, it's that negative, you know, y minus y hat, or y hat minus what is it? Yeah, y minus y hat dotted with all of that stuff. So probably take what you wrote out in your homework, okay? You'll want to put that in your notes. Just because you don't want to have to do your back propagation calculation steps during the exam. That's like, that would be a nightmare. But just like, so I mean, this is kind of like, okay, did you get your did you put this down on your things? Okay, so anyway, that's one possible thing. Okay. We can have a maximum likelihood MLE thing, and this one, it would be like it'll be a probability function with one unknown. Okay, so it'll be either so I'll give you like a univariate probability distribution, or I'll give you a univariate probability distribution with basically one unknown parameter. Okay, so it could be it could be a probability distribution that just has one parameter, or it could be like the normal distribution, but we'll say this parameter is fixed at this value. Okay, so there's only one unknown. All right. So so one parameter is unknown and must be estimated with the data. So for example, could be a normal distribution with the standard deviation held constant and mean unknown. Or it could be a binomial distribution with n constant but p unknown, or it could just be a distribution with one unknown, like an exponential distribution, or a Poisson distribution, or I don't know, whatever. Okay, one of these basic kind of probability distributions, and I'll provide the PDF or the PMF, so you don't have to memorize every single probability distribution out there. But like, if it's your very first time ever seeing like the exponential distribution, then it's probably going to be like, oh, okay, you probably should have just reviewed a little bit to be a little bit familiar with some of these things. But anyway, I'll provide some sequences of observations, okay, or some observations taken from this thing. So, if it's like the normal distribution, it'll be like you have this value of, 8 and 8.2 and 7.7 or something, okay? Or I'll provide, if it's from the binomial, I'll say, n is 20 and p is unknown, and you got 12 yeses, and another time you got 13 yeses, and another time you got 10 yeses, or something like that, right? So I'll provide kind of a sequence of these things, and then so based on the data provided, you'll find the maximum likelihood estimate of the unknown parameter, and then related to that, you'll also calculate the Fisher information. Okay, and again, definition of the Fisher information is the negative expected value of the second derivative of the log likelihood with respect to the parameter. So that will be there. Okay, and so that's that. We'll also have a Bayes classifier problem, and maybe Bernoulli binomial, maybe normal distribution, maybe both. Again, debating on which of these problems to throw in there. So you'll have data drawn from a Bernoulli distribution or a binomial distribution. It'll be like this, you got this sequence of yes or no's, or this many yeses and this many no's, or something, right? Successes or failures, however we call them. And then you have these different possible classes that your observations could have come from. And this class has this probability of success. This other class has a different probability of success. And I'll provide kind of the summary of the training data. So the training data will say, basically class A has, this is the summary information. This is the p hat for that class. Okay. And then you'll use that in the Bayes classifier to say, all right, for our observations, we think it came from class A, or we think it came from class B, or whatever it is. Okay. All right. Similar thing. This one is for normal distribution. I don't have this in. Well, I guess for the in class we've been doing a multivariate normal, and here it's pretty much the same thing, but it's going to be univariate to kind of, because multivariate by hand is a little bit tougher. Okay. And so you'll have kind of a mixture of a few possible classes, right? So, class A has mean 10 and standard deviation 1, and class B has mean 12 and standard deviation 3, okay? And then you get an observation at, say, 11, okay? What's the likelihood that it comes from A versus B? Your prior probabilities, maybe class A is, 70% and class B is 30% or something like that. And then, and so using that information, what's the probability that observation 11 comes from one of these classes? Okay, and then handful of conceptual questions, and this will cover from wherever we left off on the midterm. I think midterm was up through lecture 3.1, so now we're going to go from lecture 3.2 up to today's lecture. 6.3. Okay. All right. Any questions? We're all good? Yes.
Wait, so for like the normal PDF,
yeah,
we'll like have to punch in like not the integral to our calculator, but like the whole.
Yeah, you'll have to punch that in. Like if you want, like, for the likelihood, you technically don't need to include that front constant of 1 over root 2 pi. You do have to include the sigma, because that could be different for the distributions, right? So but yes, you will have to do e to the negative, x minus mu over sigma squared type of thing, and then yeah, you have a normalizing constant in the front, 1 over root 2 pi. Sigma. Technically, you can ignore the 1 over root 2 pi because it's going to be shared across all of the numerator values, and they'll all kind of cancel out in that way. But, if you want to kind of be careful, you can do it, whatever. Your calculator might even have like a normal PDF button in there. I'm not anti using your calculator for that. But if you don't, it's a matter of just kind of plugging in, and I'll write out the PDF for you. So, but yes, you do have to use that, and again, you want to make sure you use the PDF, not the CDF. That's going to give you the wrong answer. So, okay, let me look up our first view quiz answer. Actually, I gotta pull this up here. Okay, and then let's look at today's lecture, K-nearest neighbors. Okay, K-nearest neighbors is a classification thing, classification method, machine learning. It is I'd say it's fallen out of favor a little bit more recently. It's still useful. It still shows up a lot. But as data has gotten bigger and bigger and bigger, K-nearest neighbors, the computational expense of K-nearest neighbors climbs with the size of your training data. So as your training data gets bigger, the prediction cost of K-nearest neighbors gets more expensive, and I would say that that's one of the reasons why it's fallen out of favor. But anyway, let's talk about how it works. The reason why it's called K-nearest neighbors is because you get a new test case, and you want to predict what class does this new test case belong to? And the way you do it is you say, all right, what values in my training data are most similar to my test case? So we're looking for the nearest neighbors of our test case. And we look for, the 5 nearest neighbors, or the 7 nearest neighbors, or the 3 nearest neighbors, some arbitrary value k. We look at our k nearest neighbors, and then and we use that. So the way it's going to work is you have your test case, and you're going to measure the Euclidean distance from your test case to every single observation in your data, right? And so you get a distance. Okay, this is, so if I'm sitting here, it's, 6 feet to this person, 7 feet to this person, 8 feet to that person, 9 feet, and so on and so forth. And I measure, okay, this is how far everybody is. And then I'm going to say, okay, who are the 3 nearest neighbors of mine? Okay, so we sort them, sort the resulting distances. We select the k observations with the smallest distances, and then each of those get a vote. All right, so we say, okay, these are the 3 nearest neighbors, and who votes class A, right? Who of the neighbors, which ones belong to class A and which ones belong to class B? Maybe all 3 are class A. Well, then we're going to do class A, all right? But if 1 is class A and 2 are class B, then, with each vote, majority rules, we're going to say, okay, our test case is going to be class B. Question is, okay, let me give you your first view quiz answer. The letter B. B is our first view quiz answer. I'm nervous that I picked the wrong answers. Okay, B. Yes, indeed, it is B. B is our first view quiz answer. All right, now, performance of the model in terms of how accurate are your predictions could be affected by your choice of k. Do you use your 1 nearest neighbor, your 3 nearest neighbors, 4, 5, 6, 7, 8, 9, 10? Smaller values tend to overfit the data, and then larger values tend to maybe generalize a little bit too much. Okay, so you have the problem of underfitting. And so, what do? We often use cross-validation, and we say, all right, in our training data, when I used k equals 5, I had a 96% accuracy, and when I used k equals 7, I had a 98% accuracy, and then with k equal to 9, I had a 91% accuracy or something like that. Okay, and so we go, okay, based on these different values of k and my different accuracy values in cross-validation, we're going to pick the k with the highest. Okay, but again, whenever you do cross-validation, one of the drawbacks is it's subject to randomness, right? So you do one run of cross-validation, and it says, oh, you should go with k equal to 7. And then you do another run of cross-validation, it says, oh, you should go with k equal to 5. So that could be a problem. But probably that also means whether you use 5 or 7, it's probably okay. All right. But it could make a difference. It could make a difference. Sometimes you end up in situations where you get tie votes. Okay, so if you have 2 classes and you're using k equal to 10, right? You look at your 10 nearest neighbors and you have 2 classes. It's possible that 5 say your 5 of your nearest neighbors say let's go with class A, and then the other 5 say let's go with class B, and now you're in a tie situation. Okay, so often recommended is use an odd number k, and if you only have 2 classes and you use an odd number k, then you won't have a tie. Okay, but if k is even, then you could end up with a tie. And if you have more than 2 classes, no matter how many k you have, there's always a possibility of a tie, right? So if you have 3 classes, even with an odd number, it could go if you have k equal to 9 and you have 3 classes, it could go 4, 4, 1, 3, 3, 3, and you'll have a tie there, right? There's no set rule for how ties should be resolved, and which strategy you want to use is up to you. You can also use cross-validation to determine which strategy to use. And you could say, all right, these are the predictions in our accuracy rate when we used this strategy for resolving ties. This is the prediction and accuracy rate when we used a different strategy for ties, so you can do that. One method is you just say, all right, this is unclassified. This area and this region here, it could go either way. It could go class A or class B. So you just leave it as unclassified. You could say, all right, if we have a tie, then we're going to switch to our one nearest neighbor. There's never going to be a tie when you do your one nearest neighbor, okay? Unless, I guess if your data is discrete, it is possible that you have two observations with the exact same distance from the thing. But in a continuous thing, having two observations with the exact same distance should be probability 0. But if it's a discrete distribution, it is possible that you have two observations with the exact same distance. But anyway, another situation. But usually, one nearest neighbor, you're not going to have a tie. You can also select randomly among the groups that are tied, and then you can also, among the groups that are tied, select the group that has the nearest neighbor, which is not necessarily the same as choosing your one nearest neighbor. A lot of times it is, but not necessarily. So those are all different options. Okay. And again, this during the algorithm where you measure the distance, okay, from the test case to every single other point in the training data, that step can become very computationally expensive depending on how big your data is, depending on the dimensionality of your data as well. All right, so on the next few slides, I have two-dimensional data, and I'm going to demonstrate k-nearest neighbors. So I have intentionally left out the code for doing k-nearest neighbors because you guessed it, it's going to be part of your homework. So, and to be honest, the compute, like R already has a function called KNN, and it does k-nearest neighbors for you. So writing your own k-nearest neighbors code is a little bit silly to do in real life, but I think it's a good exercise for homework that will, like, you have to think about this stuff and really understand how the algorithm is working. Okay. All right. So anyway, in our training data looks like this. We have some red dots. We have some blue dots. And one thing is our eyes are really good at determining distances in 2 dimensions. Right? We look at this. I can put in a test case, right? So this dot represents my test case, and I want to know, okay, is this going to be class red or class blue? Okay, and very easily, like, our eyes can kind of say, like, these are the points that are closest, and I don't have to calculate the distance to these really far away points. Okay, and so you might feel like, why bother calculating the distance to every single point in the data, which is what I have on the next slide. So I've drawn, like, all of the Euclidean distances. So this feels silly in 2 dimensions, but the thing is once you go higher than 2 dimensions, now there's no way to look at a point and say, like, if you have a data point in, say, like 10 dimensions, okay, how do you know the distance, which points are the closest to this? Now we aren't really able to visualize or do anything. And so, you have to calculate the distance from this point to every point in your data, doing that, all right? We generally use Euclidean distance. I guess there's no rule against using, say, like, Manhattan distance or some other kind of distance metric, but you know, Euclidean is frequently the distance metric of choice. All right, so you calculate these distances as represented by these lines from the test point to the training point, and then you're going to say, all right, let's pick the k nearest neighbors. So if I choose k equal to 1, it's this observation. So this circle represents, you know, we don't have any other points within the radius of the circle, so this is the nearest point. And so here I have 1 vote for red, and so k equals 1 chooses red. I guess I'll move that there. For k equal to 3, this is the third closest point, and so we have a total of 3 points, and we have 2 votes for red, 1 vote for blue. So this is going to get classified as red. Okay. With k equal to 5, now I have 3 votes for blue and 2 votes for red. And then with k equal to 7, okay, so I guess this was just a tiny bit farther than this one. Okay, with k equal to 7, we have 4 votes for blue and 3 votes for red, and so this would vote blue. Okay, so here's a new test case over here. What do you think this should get classified as? Red. For k equal to 1, it'll be red. Oh, sorry, calculator distances. K equal 1 is red. K equals 3 is red. K equals 5, also red. K equals 7, also red. Yeah, so this one is kind of clearly in red territory over here. All right, let me give you your second view quiz answer. The letter E. E as an elephant. E as an elephant. You know what? We're gonna get through this. We're gonna finish early, I think. Okay, so I copied some code off of Stack Exchange, which I don't want you to do for your homework, but like if you had a job to do, I think it's okay. That's, but you know, for the homework, again, the point of the homework is that you do the exercise to get stronger, right? It's like, you know, going to the gym, lifting the weights itself, that process of lifting the weights is what makes you stronger. But, you know, if we need somebody to lift boxes to move, go ahead and hire some movers to do the job for you, okay? I think that's okay. So anyway, this code can draw some boundary regions for us, okay? And so this is the same. It's the same grid of points, okay? And what this code has done is it has created little test points at every single one of these things, and then it uses k nearest neighbors to say, all right, if I have a point at this dot, what is my one nearest neighbor? And it's going to get classified as blue, all right? And so it went through, I don't know, however many points did I have. I had around 10,000 points. So for 10,000 test cases, it said, all right, what's my one nearest neighbor? And it colored the dots accordingly. And so this is kind of our boundary region that we get, right? And then it kind of draws a line to indicate these boundaries. And so this is the resulting shape. And with k equal to 1, every dot has a lot of influence on how things get classified. Okay, so here's the boundary for k equal to 1. Here's the boundary for k equal to 3. It's a little odd, and now we see this red dot gets kind of misclassified, and this blue dot ends up misclassified. But this is kind of the border between the red side and the blue side. Okay, with k equal to 5. It becomes like that, and k equal to 7, it draws like that, okay? So as you increase your k, the border becomes, smoother isn't the right word, but it becomes less influenced by individual points, okay? So this one point isn't going to suddenly draw the border out like this, okay? so as k equal to 7, you're still going to get a little bit of jaggedness, but it's going to take like multiple points to kind of move the border. Just having one extra point over here is not going to affect the border as much. Okay, similar kind of thing, but now I have more data drawn. So here, now there's kind of this, the red and the blue are a little bit more mixed, and so you can't, so what does it look like? Well, if you did k equal to 1, every single dot kind of will not get misclassified, and you get all of these, you get, this weird shapes, right? So these are, you got these enclaves and exclaves. It's like that piece of Russia that's in Eastern Europe that's like that borders Lithuania or whatever it is, Kaliningrad. Do you know what you're talking about? And also, or like in Spain, or actually on the south of Spain, Great Britain owns like a little piece of, they own like Gibraltar. And it's like these little like colonial territories, right? And so, like your primary country is over here, and then you got, you have like territorial influence because, you sent your troops to take over this land over here or something like that, right? And so with k equal to 1, you have these, these exclaves. Okay, but as soon as I bump up to k equal to say 3, okay, these little red dots or whatever isn't enough to kind of hold on to, I guess, the territory. You get like a little bit of like weird things here. Like here's a dot right here where it's like, oh, the 2 nearest neighbors are these 2 red dots, and this blue dot. The 3 nearest neighbors are these, and so this actually gets classified as red. So you still get a little bit of weirdness between some of these things, but overall, I would say the border between k equal 1 and k equal to 3, you get, again, less influenced by individual points, right? So these blue dots that have kind of gone out into red territory, they don't get their thing, and these red dots don't really get either. There's kind of like this, there's not a whole lot of like blue presence over here, so these 2 dots actually get to hold on to a little bit of space over here. But as I, bump it up to k equal to 5, now you get kind of a little bit more of a clearer boundary. Again, smoothness isn't the right word, but, less influenced by just 1 or 2 kind of stray or, individual dots out there, okay? For k equal to 7, it looks like this. K equal to 9 looks like that. And so now you start to get kind of more of a better defined boundary. Here's k equal to 15 and k equal to 21. And k equal to 31 at this point, okay? So as we've bumped up the k, you get kind of a boundary that's more, I guess, clearly defines the sides or divides it and is not influenced so much by odd points here and there. Okay, actually, I think that's it. But k nearest neighbors, again, it's still very popular, and it's still quite a bit useful. Again, but once you start climbing over, say, like 10,000 observations in your training data, then you probably want to move to something else because I guess you're going to have too many things to check against. Yeah, I guess one strategy you can use if you have a lot of observations is if you can pick like archetypes of a certain class, or your class, you can say like, okay, I've got 100,000 of these things, but we're gonna say these 1,000 observations will represent class A and class B very well already, and I don't need to have the other 99,000 observations, which are really just tiny variations of these these core 1,000 individuals or whatever, right? And so you could say, okay, these 1,000 are going to be really just the values that I use in my to kind of measure distances, and this is good enough. And then you can kind of limit the computational expense so it doesn't kind of, but how do you pick those things? That's a little bit like, that's tough. So, do you just say, okay, well, I'm just going to randomly pick 1,000? Well, then it's really, there's a lot of like, you thought the random influence in, K, why do we love to use K for everything? K-fold cross-validation was bad. If you're going to say, all right, these 1,000 observations are now my, the ones that I'm going to use for classification, now it's really subject to like whoever ends up in those whatever 1,000 cases you have there. So, okay, but that's K-nearest neighbors. Hopefully the homework assignment where you write a little bit of K-nearest neighbors code is not too awful. And you don't. I think in the homework cases you don't even have to. Don't worry. You don't have to worry about ties and stuff. Just just go with that. Okay, we'll go ahead and end here. Last letter today is D. D as in dog. D as in dog is our last view quiz answer. And we'll end here. Have a great weekend. We'll see you next week.